I'd like to say welcome to all the people that are participating in our webinar today. We have Dr. Brian Theroux, who will be speaking to us on Plenoptic Cameras, the future of imaging. After a few introductory remarks, we'll turn it over to Dr. Theroux, and then we'll have a question and answer session at the end of the webinar. The webinar will last approximately 1 hour. All webinar participants are initially on mute, so if you have a question, please unmute yourself during the presentation by clicking on the green microphone button on the dashboard. If you do not have a microphone, you can submit your question on the dashboard in the comment section, and Vicki will read your question to Dr. Theroux. The webinar will be recorded, so if you have colleagues that's not able to participate in the webinar today, they'll be able to view it on the Auburn University Research Advisory Board website, and you see the website pictured here, and Vicki will send the link out at the end of the webinar along with a short survey. Today we're glad to have Dr. Brian Theroux. Dr. Theroux is the W. Allen and Martha Reed Associate Professor in the Department of Aerospace Engineering at Auburn University. Dr. Theroux received his BS in 1999, MS in 2001, and PhD in 2005 from the Ohio State University. He established the Advanced Laser Diagnostics Laboratory at Auburn in 2005. His research program is focused on the development of high repetition rate in the order of 1 megahertz optical diagnostics for turbulent flow measurements, and more recently, the development of Plenoptic camera technology for 3D flow visualization. His research has been sponsored by the Army Research Office and Air Force Office of Scientific Research, both of which started with Young Investigator Program grants, as well as the Office of Naval Research and National Science Foundation. Dr. Theroux, we'll turn the webinar over to you at this time.
All right, thank you, Rodney. I'm assuming everybody can hear me?
I can hear you. You're good.
Okay, good. Didn't want to speak for 30 minutes and then find out you're just staring at a screen. So I'm definitely excited to be able to talk to everyone. I've been working on this stuff for a while now, and you know, hopefully as you get to meet more faculty, hopefully they're all passionate about what they're doing and excited to get a chance to actually share what a lot of you have supported over the years. So I'm definitely excited to talk about this. A little bit is just in the past couple months, I changed the name of my lab to the Advanced Flow Diagnostics Laboratory. We took the laser out of it because with this new imaging technology we're working with, we don't need lasers as much as we did. But this first slide here just gives an overview of what my laboratory is about, and then highlighted in orange there is sort of the subtopic that I'm really going to focus on this presentation today. And I'm definitely going to try to keep my speaking down to about 30 minutes or so and keep it on the highlights and some of the more entertaining aspects of what we're doing. But really what I've built my lab on here is the development and application of really the next generation of optical diagnostics. My background is fluid dynamics, experimental fluid dynamics, so a lot of these diagnostics are specific for fluid dynamics, but what's really exciting about the Plenoptic camera that I'll describe is I really think this is something that can be applied to a lot of different disciplines. So in terms of unique capabilities in my lab, the highlight here is light field imaging with Plenoptic cameras, where we use tomography to do 3D imaging. So I'm going to talk a little bit about that, but just to talk about some of the other things just really quickly. When I first started, one of the first things I did was I built this laser system which produces these high energy laser pulses, but we can do it up to 1 million pulses per second. And we use that with high-speed cameras that can also image things at 1 million frames per second. So we've looked at supersonic turbulence, things that are moving. I like to think of it in terms of football fields. 10 football fields per second is some of the speeds of the flows that are encountered in a lot of practical military systems, particularly ones that will be in the future. We also have a lot of experience with some other techniques, particle image velocimetry, background-oriented linear imaging, and laser-induced fluorescence that are commonly found in a lot of labs, not only in the U.S. but around the world. So these have sort of become conventional, and what we're trying to do is take these techniques that are quite common and familiar and really push them into the next generation by extending them from traditionally 2D measurements to 3D. And so in terms of research areas, how I use these capabilities, one is the development of the instrumentation itself, but also is to study these problems in fluid dynamics, turbulence, compressible flows, air optics, flow control. I've had a number of sponsors, fortunately, throughout the year. Air Force Office of Scientific Research, Army Research Office, Office of Naval Research with big DoD presence, National Science Foundation. More recently, I've started working with some of the national laboratories that they're interested in taking this technology and applying it in their labs, a couple of commercial companies that are related to this, and several different universities. And just to preface this, as I talk a little bit about my laboratory, just the nature of my work, which is developing this instrumentation, is partnering with people that need the instrumentation. Because I think you can only be an expert at so many things, and I've chosen to be an expert at the measurements. It's critical that I partner with people that need those measurements. And so I've been pretty successful at establishing a number of relationships, but I know one of the purposes of this talk is to see how you guys might be able to support me. Really, it's coming up with these partners, coming up with these collaborators that have an interest in this technology, and just starting that dialogue and that conversation. And so I guess moving on. Okay. So to sort of talk about what's unique about this technology, and please interrupt at any point. I'll be happy to answer questions as we go. We need to define what is light field imaging. And light field imaging is, it's taken this concept that's actually over 100 years old, but it's only been in the last decade that people in the scientific community have even begun discussing it. The idea of a light field is, it represents the complete spatial and angular distribution of light in space. You might think of it like an electric field or a magnetic field where you have this property defined throughout space. Well, a light field is keeping track of all the light rays that are traveling in space. And a conventional image is just a 2D sampling of the light that is truly traveling through a volume. And this concept in the last decade has really been embraced by the computational photography community. And these images that you're seeing here are examples of what that community has done with the light field. They basically have taken this idea and said, instead of just recording these 2D projections of a scene, let's record much more fundamentally what a scene is about. And if I have a light field recorded, and we'll talk about how a Plenoptic camera does that in a minute, I can then go afterwards and on a computer generate what a conventional image would look like. So on the top here, this is an image taken in my laboratory. We have a number of cameras and different components laid out on the table. And with one camera, we took one snapshot, and because we're recording the light field, we can generate these images that are refocusing from this camera in the front all the way to this set of notes in the back. And whereas on the bottom, another similar image, we can change the viewpoint that the viewer is visualizing what is going on. And again, the emphasis here is this is all a single snapshot. And so for my community in fluid dynamics, where things happen extremely fast and we need to essentially do strobe photography or very fast photography, the fact that all this information is recorded at once gives us the opportunity to turn this into a 3D diagnostic. There's a lot of ways to record and capture this information. One of the more intuitive ones is just to have an array of cameras or a camera on a gantry where you move it around. And one of the early pioneers in this work, they actually went to one of Michelangelo's famous statues, and they took an image of that statue from it was like 1,000 different viewpoints. And the reason they were taking an image of this stature from 1,000 different viewpoints is they wanted to archive digitally, so essentially be preserved forever, the exact 3D shape and features and textures and characteristics of that statue. Practically, though, the problem we run into is we don't want 1,000 cameras sitting in our wind tunnel. We don't want 1,000 cameras surrounding that jet engine. There's a lot of flow fields where you can't have more than one camera looking into there because you have very limited optical access. So what really appealed to us was this idea of a Plenoptic camera. So to give you an idea of what a Plenoptic camera is, this is just a photograph of the Plenoptic camera we built in our lab. And for all intents and purposes, this looks like any other camera that you would find in a laboratory, in industry, on an assembly line, even handheld photography. There's not a huge amount of difference between our camera and those cameras. The only difference is what is seen here is we developed this apparatus that allows us to locate a micro lens array very near the image sensor. And in this case, the micro lenses, they're each 100, they have a focal length of 500 microns. They're separated by 125 microns each. So on this prototype sensor, we have about 300 by 200 micro lenses overlaying on top of this image sensor, and they're positioned 500 microns from the image sensor. And we've recently built several cameras that more than double this resolution, so we're moving up with that. But physically, this is what the camera looks like. And like I said, the motivation for it is, this is an experiment we recently done at Illinois where we're doing 3D flow. This is a water tunnel, and there's a hemisphere here that we're looking at the flow over that hemisphere. This is all the instrumentation we need to do a 3D measurement of that flow. The competitive system that if this technology didn't exist, or if we weren't developing it, is you would find something that looks like this, where we see 6 different cameras surrounding that flow. And so you can get an idea for the type of optical access you need to apply this type of measurement. Each of these cameras is, has to be precisely aligned and calibrated to the other cameras. So if one of them gets bumped, it can throw the whole system out of alignment. It's much more expensive to buy all of these. It's a much more complicated process, whereas our technique is a single camera. So really the main attraction for us was this ability to acquire 3D data with just a single camera. Now the focus of, I'd say, the next 10 minutes or so is how we're using this technology to do particle image velocimetry, but I wanted to reserve the last 5 to 10 minutes of the talk to sort of talk about the future and where I think this technology is going to be moving over the next decade. So let's look inside the camera a little bit more and how we're physically doing this, what is actually happening. So here we have a conventional camera, a schematic of how a conventional camera works. We have a lens, and that lens is mapping some object plane onto an image plane inside of the camera. And when you focus the camera, you're physically adjusting this distance between the main lens and the image sensor. And if an image is out of focus, it's because this image sensor is either in front of this focal plane or behind the focal plane, and you get a blur spot. This is an effect we're all familiar with and have seen. They use it to dramatic effect in movies when they adjust the focus and they focus on the person talking, and then they refocus to the person standing behind them with a knife or something like that. So any ability to refocus an image is mechanically done. Well, with the Plenoptic camera, we take the same basic structure, but our only addition is we add this micro lens array right in front of the image sensor. Now, the function of the micro lens array is to take a subset of the angular information that is striking that micro lens and to focus it onto one pixel behind the micro lens. So this pixel, highlighted in green, is capturing all of the light rays that are traveling along this path through space. But if I move to the next pixel, because of the optics, because of the way we configured the optics, this pixel is capturing all of the light ray that's traveling along this blue path. And so as we move along from each pixel to the next, we see that this collection of pixels behind the microlens, it's recording all the same information that a conventional camera is recording, but now it's discretely measuring the different angles of information coming into the camera. So this is what a typical Plenoptic image looks like. And this was actually one of the very first images that we collected. This is just some of my son's Star Wars Lego figures. So the dimensions here is this is probably about an inch to an inch and a half high, and this is probably 2 to 3 inches wide. When we just look at the image like this, we see Darth Vader. His face is in focus, but we have these characters that are sort of blurry in the background and in the foreground. But if we zoom in, say on the handle of this lightsaber, now we can see the effect of these microlenses. So each microlens represents a different position, but each pixel behind the microlens represents a different angle of light that is striking that microlens. So we can go through this image and pixel by pixel figure out what the position of the light ray is that is hitting the pixel and what is the angle of the light rays that are hitting that pixel. When I have that information, I can now do things like refocus the image. So whereas before everything was coming from all these pixels corresponded to one focal plane, I can now take a different collection of pixels. I can combine pixels from different microlenses, but I can choose them such that they all correspond to light that is coming from a new focal plane. So originally I was focused on this world focal plane. I can now reassemble all my information to focus on a new focal plane. And when I do that, we can then generate this ability to refocus an image as shown here. And if the movie isn't playing well on your screen, I just pulled out a few shots from there that you can see on the left here. But you can see this ability to focus on the stormtrooper in the foreground, the C-3PO in the background. And again, I can't emphasize enough that the real appeal to us is this was a single snapshot from a single camera. So it really is a point-and-shoot type of capability that we're working with here. The biggest trade-off you'll see is that each of these images has a relatively small resolution. That's something that's going to come with time, just as image sensors get to have higher resolution, and as this technology is more embraced, there really is no fundamental limitation why we couldn't build gigapixel image sensors today for these type of applications. The main thing is the consumer demand for such sensors. And I can definitely expand upon that if anyone is curious. Here's just another example of a refocused view, and the reason I chose this example is we're not constrained to just looking at things that are a couple inches by a couple inches field of view. We can take a setting like this and we can refocus on over quite large distances. And that will be important later when we consider applications like rangefinding or trying to find out how far away objects are in a scene. But you can definitely see what I think is this really gee whiz capability. And there's a company called Lytro. If you go to Lytro's website, it's lytro.com. They are building consumer versions of these cameras. They actually invented the technology. We're trying to adapt it for more scientific research purposes. But they're focused on the consumer market. So you could go today and buy one of these cameras, take a picture of one of your children or grandchildren playing soccer, and then do a cool effect here where you could focus on their face and then focus on the ball going through the goal. I'd love for Auburn to buy one of these cameras and use it at a football game. They could really do some amazing sports journalism with some of this technology. Perspective Shifts does a similar thing, but instead of combining, so here's a microlens image that we just saw before. Instead of combining different pixels of information, if we reconstruct an image just using one pixel from each microlens, and what we can see here is each microlens sort of sees the edge of this lightsaber handle at a different location, we can then generate a change in view like this. And you can take these images and do 3D imaging, because most 3D cameras just have 2 images. We have an entire array of cameras essentially looking at this. And then again, this image as well. So this is just generated by just choosing 1 pixel behind each microlens and shifting which pixel we look at. So the question we asked ourselves when we started doing this work is, can we use this technology for other purposes? And originally it was for flow diagnostics. So the approach we came up with is to use this information contained in the light field and our recording of the light field to reconstruct a volume of particles. So one of the most common techniques in fluid dynamics is known as particle image loss symmetry, because it's very difficult to see air or any gas move. What is typically done is smoke or some other particle is seeded into the flow. And a lot of times these smoke particles might be 1 micron in diameter, so they're so small that they will respond to even the smallest gust of wind to follow the turbulent flow and everything going on. And so we wanted to know, if I have a volume of particles that is illuminated on the camera, can we reconstruct that volume? And then if I can do this for a pair of images, then I can figure out where those particles have moved, and then I can figure out what the velocity of the flow is. Well, to do that, we have applied some principles we've learned from the tomography community to do that reconstruction problem. So here's a typical Plenoptic camera image of a particle field. How we know a PIV image is good is if you can't tell anything about the flow from it, because you want the particles uniformly distributed. And what you see when you look at an image like this is you sort of see this random distribution of particles. And if you zoom in, it sort of looks like a chaotic mess. But the pattern that's forming here is the direct function of how far away the particle is from the camera. Now, if a short time later, and we can do this actually within 1 microsecond apart, and I don't know how well this is going to translate here, but I'm flipping from image A to image B. These are separated by only a few microseconds. We can see some of these particles move. So that's how we get the fluid motion from here. So for example, if you look at this little particle blob here, you can sort of see where it goes. So that's the problem of tomography and reconstruction, is how do we take this information and generate a volume of particles? So we've developed a lot of tools to do this. We can generate these images synthetically so that we know precisely what particles are. We've done experiments as well. But we set up the problem basically like this, where we have this volume we would like to reconstruct, which has 3 dimensions. We have this image, which I show here with 2 dimensions by pixel coordinates, but actually it's really 4 dimensions because we have the position and the angle of light rays. And then we have this weighting function, also known as a point spread function, that describes the relationship between this volume of particles and what their projection onto the camera looks like. And then we use this algorithm called the MART algorithm, which stands for Multiplicative Algebraic Reconstruction Techniques. It's an iterative method to basically cycle through possible solutions of this volume until we find the best match. And so on the right here is just an example for how well it works. This is just a very small volume that we simulated of particles, and this is where we have deduced, based on this algorithm, where the particles are from a reconstructed image. So we can compare where they really are and where we think they are using this type of thing. One thing you'll notice is that our particles end up being a little bit elongated along the axis that the camera is looking. So one of our limitations is that the resolution in the depth direction, the resolution in the direction the camera is looking, is not as good as the resolution in the lateral directions. But what we found is that the motion of those particles is still quite accurate, and I'll show some examples of that. It was interesting as an experimentalist, though, to come into this, and all of a sudden I found our biggest challenge was the computational challenge. It's not the experimental challenge. It's not setting up the camera, running the wind tunnel, or anything like that. it was really taking a problem where we have 11 million pixels of information. A nominal volume size might be 300 by 200 by 300, maybe smaller, where we have 18 million volume elements. So technically, the size of our weighting matrix that connects every point in our volume to every pixel in our image would be a file size that is 400 terabytes, which is just not practical for us to work with. Fortunately, most of those values are 0, but we're still left with file sizes that are on the order of up to 500 gigabytes, which is too large to store in memory on the desktop and gives us I/O limitations. So right now, the state of the art with what we're doing, and we focus on desktop applications because we're thinking about the user of this who's in a lab and might not have a cluster easily available. It takes us about 30 minutes per image to do a full reconstruction of a volume. So getting into some of this synthetic data and results, one of the things that we simulated synthetically was known as a Gaussian ring vortex. If you go to a science center with your children and or you like blow a smoke ring out of your mouth, you'll see basically what is known as this Gaussian ring vortex, and it's just this ring of vorticity like that. We simulated a particle field with those characteristics, and we reconstructed a particle field with those characteristics. And so what we found is that we can track the motion of these particles to better than one voxel. A voxel is like a pixel, but in the volume, to quite good accuracy. We then went to our wind tunnel and tried this out, and we just looked at the boundary layer flow. This figure here is actually showing what's known as a Stratford ramp, and what we're simulating is the flow that you would get on a wing, where the flow is going to separate, and that can lead to stall. It's the primary source of drag on a lot of air vehicles. And so we're simulating some of the characteristics that a boundary layer flow is subject to on those type of things. And we just have a laser that illuminates a volume. In this case, the flow is moving along the wall. We just seed smoke into it. And this is a typical example of what we can measure with this. So in this example, the flow is from left to right. This is the high-speed flow in the wind tunnel. This is the low-speed flow near the wall of the wind tunnel. And we're just, afterwards, running a slice through the flow field, just sort of looking at some of the 3D features of what's seen there. So without going into the details of the fluid dynamics, I'll just say we were quite pleased to see a lot of features that we really expected in these flows, and this is a valuable tool. Another example is we took this camera to the National Center for Physical Acoustics at the University of Mississippi. This was related to another project we were doing with them, but we figured we were developing this camera. Let's just spend the day seeing if we could get it to work. Well, here's a picture of the facility that they have, and what's unique about their facility is this is a supersonic jet. In this case, it's a Mach 1.74 jet. The jet diameter, you can see the jet nozzle here sort of in the center of this black and white image. It's a 2-inch jet diameter, but the flow prior to expanding through this jet is heated up to about 1,300 degrees. So what they're really trying to do is simulate the exit conditions of a typical military fighter jet engine. The Navy's particularly interested in this, to understand how this jet produces noise that goes into the environment, because a lot of these sailors have noise-induced hearing loss because they're on the deck of an aircraft carrier. They can't get away from it. They have to be on the deck, and as these things take off, they're exceedingly loud. If you've been to an air show, you know what I'm talking about. And so if you're exposed to that day in and day out, it can be a problem. So we just took the camera and we just wanted to demonstrate this is a challenging flow. Can we make a measurement in this flow? And the answer is yes. In a single day of experiments, this was just an add-on to a different project. Without really optimizing a lot of things we would typically optimize, we were able to generate this 3D image on the right here. And what this image is, it's a little volume at the exit of the jet. So the jet is flowing in this direction. The color indicates the speed. The dark red here is about 800 meters per second, so 8 football fields per second. And we can see several cross sections of what that jet flow is doing. And so our hope in the future is to go back and combine this with their acoustic measurements to sort of see how different features that we can observe might be related to the sound, and then eventually to tie flow control mechanisms into it so that we can reduce the sound substantially. So sort of the pause there before we move on to just a couple other things. This technique we call Plenoptic PIV. Its strengths are it's a 3D flow visualization method, which when we're talking about fluid dynamics, 3D is extremely important. It's a single camera technique, which I show we don't need tons of instrumentation to make this work, and it's very versatile because it's a single camera technique. The weaknesses right now is because of that microlens array, we do trade off traditional spatial resolution to get that depth information. We're still battling some of these computational challenges, and really until more and more labs get these cameras, it hasn't quite reached the critical mass yet to get up to the level of development that a lot of the competing techniques are. Some of the current funded collaborations that I have working on this camera and applying it is I've been working, this is an NSF grant with the University of Illinois Notre Dame. We're looking at turbulent flow over porous media. And one of the PIs on that grant is actually in their geology department because they're interested in riverbeds that are flowing over, they're interested in river flows that are like over gravel riverbeds, sediment transportation, where truly the flow is moving into and out of this riverbed. And a lot of fundamental fluid dynamics are based on a nice, fixed, impermeable, flat wall. And so we're looking at effects of roughness and porous walls. More recently, the contract just got in, and what's exciting about this contract with Florida State, Ohio State, and Texas is this is actually a 5-year effort. So that's a big deal because it allows us to really focus and make real substantial progress on this problem. We're looking at shock boundary layer interactions. So in a lot of Department of Defense problems, even in the commercial world, if we start talking about supersonic airliners, anything where you have supersonic flow, a major challenge is dealing with the interaction of the boundary layer flow with shocks that are also generated in the process. And a lot of those are very highly three-dimensional flows and problems. So we're starting to apply the unique diagnostics that we're developing to that problem. We're also building a camera for Sandia National Labs where they look at the dynamics of particles. Their applications, you can conjecture a little bit about what they're interested in. And we've had some preliminary discussions that, to be frank, haven't been as fruitful as I would have hoped yet about commercializing this technology. But a reason I'm really excited to talk to this group is really the future of this technology. I'm working on developing several new collaborations, and what I have listed here are actual proposal titles that have been submitted or are under development. For those of you that don't know, most of the success rate of a proposal submitted to the National Science Foundation is about 15%. So even if these are all great proposals, the likelihood, statistically, only a handful will be funded. But we're going to continue to push on all these fronts, and hopefully they'll all be funded eventually. But it just gives you an idea for the range of problems that and collaborators that have an interest in this. For example, Michigan State, we're looking to study the flow in blood vessels and how the introduction of the stent can help control or facilitates the curing of the healing of an aneurysm. With Iowa, we're looking more at maneuvering wings. Some of this is biologically inspired, flapping wing flight, but a lot of the UAV development and drones, if you're talking about any vehicle that is going to undergo any sort of maneuvering, it quickly becomes a very three-dimensional problem associated with vortex shedding on those wings. Steady level flight is the easiest condition, but as soon as you get to maneuvering, it's a much more complicated flow field. So I'm working with a colleague at Iowa. We're trying to develop some ideas to measure some of those 3D flow. Another group at Ohio State, more motivated by rotorcraft problems, is looking at dynamic stall events on rotorcrafts and applying flow control mechanisms to mitigate dynamic stall. More recently, I started talking with Litro, who's really a pioneer in the development of this technology, for how we can do range finding for intelligence and surveillance. Where the interest is there is there's definitely people in the field that want to take an image. It could be a soldier that's several hundred meters away from somewhere, and from that image, he wants to know exactly how far away different objects or targets might be. Also been talking to Notre Dame. They have a huge facility that studies gas turbine engines, and some of you might have seen a recent headline. GE Aviation started a research center of excellence in affiliation with Notre Dame in that facility. We're starting to talk with them, or we've been talking for a year, on how we can actually look inside their engines and their compressors and gas turbines to make measurements inside those engines. So these are all ideas that I'm actively trying to cultivate and grow, that if I'm lucky, they'll be funded in the next few years. Some other ideas that we'd like to apply this is looking at 3D imaging of shock waves. I really want to start to look at the reacting flow community, the combustion community, multi-phase flows, hyperspectral imaging. There's no reason we can't go to infrared, UV, high-speed cameras, and some conversations later with what GE Aviation is trying to do in Auburn, is there's a lot of reason to believe that this technology can be really used to enhance and assist the additive manufacturing process. So just about 6 or 7 more slides, and these are just sort of progress reports on these. When I say we're trying to get into flame imaging, it means we're going in the lab and we're lighting up some Bunsen burners, and we're taking our camera and we're looking at what's going on. And as an example, as part of this, we're trying to develop much faster algorithms to do this 3D reconstruction problem. So here on the left, we have 2 flames. This is an example like this, where we have this flame in the foreground, we have this flame in the background. One thing we can do with this camera is we can refocus it. So I can focus on this flame or I can focus on that flame. But the problem is, if I'm focused on this flame, which we see here, the other flame is tremendously blurry. Now, if these were on top of each other, it would be very difficult to tell what is in focus versus what is out of focus, because a lot of characteristics of flames are sort of diffuse anyways. So we're starting to develop algorithms to account for this problem, and on the right is a very preliminary result where we can really see that we're able to remove a lot of this, basically know that this is out of focus and know that it doesn't belong in this image, and remove it so that we get a better look at what's going on there. We're starting to look at multi-phase flow, and our motivation actually for this has been the Navy is interested in these things. But a challenge with diagnostic development is the funding lags behind the development effort, usually by a couple of years. There's a lot of people that have good ideas for how to do diagnostics. They're not going to fund it until you show a pretty good potential and promise that you're going to really change the way they do measurements. And so that's definitely one challenge I face quite a bit, is we have to do quite a bit of legwork before we even get to the funding proposal writing stage. So in this case, we just bought an aquarium, and we have just traditional aquarium components, bubbles rising, and so we're starting to look at that. My colleague at Notre Dame sent me an old damaged compressor rig that they're studying, that they're looking at there. And so we can see that here this is the most optical access you're going to find in any working rig. So the neat thing about the facility at Notre Dame is they can test actual compressor hardware and designs. It's not a, so it's at the design conditions, at the design Reynolds numbers and flow rates and everything else. And so they're starting to play around with the idea of putting optical diagnostics in there. And so they sent us this rig, and we're starting to do some imaging to see what can we do in that type of thing. So we can see the compressor blades here and the camera looking through the window. Real simple proof of concept. This just shows we can see the blade, we can see the blade shape with the camera, and we can show the ability with this single camera to sort of sweep around and look at what's in there. And what we're excited about is the camera is fast enough, and with laser or strobe illumination it's fast enough. We can get this precise of a timing that this blade could be moving at 10, 100,000 RPM, and every single time we could get the position of the blade to be in the exact same position as that blade passes around the compressor rig. So that's something we're hopeful that eventually we'll be able to apply this type of diagnostics to see what's going on in this channel actively. Rangefinding, this is actually an undergraduate student project. Really good undergraduate student working with me over the summer. I showed some of these images before. He's been developing an algorithm how we can take this image and we can extract from that image how far away objects are. And so this is the result of what he's done so far. We can see my students standing in the background, as well as some of these other objects. They're shaded blue, whereas this hat and this box are a little bit closer, so they have a different color. This pen is even closer. And we see the same thing here with the books, and even these books we can see some slightly different shades, trying to figure out how accurately we can determine the depths of things. So from a single image, we can find out how far away things are. And that can be interesting for machine vision, robotics, where you could envision some sort of robot or drone using a system like this to interact with the environment that it's in, because it can see an object and know exactly how far away it is. And it could be a more robust, stable platform than some of the stereo cameras. And then the last concept I want to introduce is this idea of multi-spectral imaging. So this is sort of another schematic of a conventional Plenoptic camera. I got this lens, it's collecting information from this point, and it's focusing it onto these micro lenses, which are just shown here as pinholes, but it's the same effect. Well, if I slide a color filter in there along the aperture of this main lens, I can now encode each angle with a different spectral content. So now, instead of each pixel representing a different angle of light, each pixel now represents a different color of light. And this is sort of the idea of what that glass element would look like. And there's a world of applications that use multi-spectral, hyperspectral imaging. Again, we have this nice, simple, compact package that can do a similar thing. You can also make this an array of polarization filters, ND filters. There's all sorts of ways you could encode different information about a scene into this same package. We're continuing to develop hardware. We recently built 4 new cameras. 2 went to Florida State. We're building another one that's going to Sandia. There's no reason we can't build infrared, UV, or high-speed variants of this. The main limitation is the sensor resolution of those. And with that, I did take up a little bit more time than I wanted, but we're under an hour, so I will stop and happily take any questions that you might have. Thank you.
Questions for Brian? If you do not have a microphone, you can go to the dashboard and type in your question, and Vicki will read it to Brian.
Go ahead.
Rodney, this is Dan Graves. I'd like to thank everybody for attending and incredibly interesting in the oil and gas industry. I know there's a lot of worry today with all the new multi-phase products that have to be measured in at the well site and at various spots in the midstream. There's a lot of effort going into that, so that might be an area that Dr. Theroux might want to look at as high probability. The other question I have, you mentioned, Dr. Theroux mentioned what might be closest to the market. What are some areas that those of us who like to see things go to market might look at and help him or better understand what's closest to the market?
Do you mean in terms of commercialization of the technology?
Yes, sir.
Well, right now, there's only 2 cameras that are making and marketing these, or 2 manufacturers. One is Litro, and they are really for the most part focused on the consumer version of this. They want people that are going to walk into Best Buy and eventually buy these cameras. The other company is called Raytrix, and they're based in Europe, and they've been trying to target the machine vision community, so sort of these inspection lines where you could take an image of a part and inspect it in a more three-dimensional sense. So those are the 2 examples that of current commercialized efforts. For me, the challenge, I'm trying to work with this company, Dantec, to market the fluid dynamics aspect of this. That market is just too small. You know, they might sell 10 to 100 systems a year. I think if they sold 100 of these systems a year, that would be a very good year for them. And that would be selling these cameras at $25,000 to $50,000 a piece. But if there was a market that was interested in buying thousands of these, you could easily get the price down to a couple $1,000s a piece. That's just an area I need more conversations with people like you to figure out where is that market and who's interested in doing that.
Thank you.
Brian, we have a question from one of the attendees who's interested in this technology for navigation. Are you familiar with any research that's been applied this technology to navigation?
No, not really. I think one of the challenges is as an object gets exceedingly far away, your ability to resolve something that's, say, 4 kilometers from 3 kilometers away isn't very good. You might be able to do that with the precision of a few hundred meters. So techniques like LiDAR and some of the other sort of range-finding things might be a little bit better there. But when things get closer, I'd say within the 10 meters or closer, this is where it might be more competitive with navigation systems that need information more in that closer range. I do have a proposal submitted with Litro to investigate the potential of looking at things further away. So there's some work being done there, but it's just not very public yet. But potentially it could be.
Any more questions?
Okay, Brian, thank you for your presentation. Stan, would you like to say any additional words? Stan Grave chairs the committee that conducts these webinars in the Research Advisory Board.
Well, first, I always want to thank Rodney and Vicki, because we don't do it as a committee. We have wonderful folks like Rodney and Vicki who help coordinate this and actually do this for us. We hope that it is an opportunity for Brian and the other presenters to get to know us and hopefully find ways to enhance your research opportunities at Auburn and Auburn research in general. I always get blown away with what wonderful science is going on at Auburn at every one of these things, and come away feeling pretty dumb, really, at the end of the situation. But again, I'd like to thank all the participants and the presenters, the presenter, and Brian Thoreau and Rodney and Vicki, and I think that's about all I've got for today, Rodney.
Okay. Thank you, Stan, and thank you, Brian. This webinar was recorded. It'll be available on the Auburn Research Advisory Board website, which is part of the OVPR's website. Vicki will email a link to you. So if you have colleagues who may be interested in this topic but was not able to participate in the webinar, please pass the link to them. If you know of other people or organizations that could have interest in Brian's research topic, please let him know. Vicki can get you his email address if you don't otherwise have it. There will be a short survey that will be emailed to you following the webinar. We ask if you take time and complete the survey. And our next webinar is scheduled for September 10th, and I want to thank everybody who participated today. Thank you very much.
Rodney, I have one more person who has a question.
Okay.
Are you still there, Dr. Thoreau?
I am.
Okay. It says, do algorithms currently exist that track feature points in captured plenoptic images and measure their depth?
Yes, and that is more or less how we're coming up with our depth estimations now.
All right. All right. I think we're good.
Thank you, everybody who participated in the webinar.
Thank you, everyone.